All right, so we're going to talk about the essence of calculus and what we're really trying to do in calculus. So I want you to think about a speedometer. I want you to think about when you're driving down the road and you want to figure out how fast you're going. So if you look at your speedometer and it says 60 miles an hour, what does it actually mean? Does that mean that you're going that exact speed for an entire hour? So if you're driving down the road and you're going 60 miles an hour, does it stay constant for a long period of time, or does it fluctuate? So I want you to think about at 2 o'clock, say it says you're going 60 miles an hour. At 2:05, could you be going a completely different speed? Well, yeah, of course. In fact, what about at 2:02 or at 2:01? Or what about even half a minute after 2 o'clock or half a second after 2 o'clock? At any of those moments, your speed could change and you could be going a different speed, right? So what does 60 miles an hour really mean? Well, it means over time, if I take the distance traveled at the beginning at 2 o'clock and the distance traveled at 3 o'clock, and I divide it by the amount of time that it took me, that I will see that I went 60 miles in 1 hour, right? I divide the distance traveled by the time that it took me, and in this case it'd be an hour. And so 60 miles an hour would be on average, I went 60 miles in 1 hour. But your speedometer doesn't actually tell you an average rate of change. It tells you the rate of change at that exact moment, at that instant, how fast you're going. So what if you didn't have a speedometer and you wanted to figure out how fast you were going? You know, let's think back to the world when I was a child and we didn't have a cell phone that we could just download a speedometer app that would tell us, right? How did we figure out how fast we were going? Well, I actually did own a car that did not have a working speedometer, and this is what I would do. At a certain time, so let's say at 2 o'clock, I would look at the mile marker that I was at, and so let's just call it mile marker 0 because that's just easier, right? So I'd say at 2 o'clock, I'd go mile marker 0, and then say at 2:05, I would see what mile marker I was at, and then I would calculate my speed, and that would help me figure out how fast I was going. So how would we actually calculate that? Well, let's think about that. Okay, so we would take our distance at the end, right? So say I was at mile marker, let's say I was at mile marker 27 at the end, and at the beginning I was at mile marker 24, and it took me 5 minutes to get there. So this is my distance at the end minus my distance at the beginning, which is my change in y, right? Over my time, which is my change in x, okay? And then I would figure out how far I went, or how fast I was going, sorry, how far I went in the amount of time, and this would give me miles. And in this case, this would give me minutes, but I can change that to hours, right? So I can find miles per hour. So let's mathematize that a little bit. So my distance, say at 2:05, say I want my distance at 2:05, this is how far I was at 2:05, minus my distance at 2 o'clock. So this is my ending point, this is my beginning point, over the amount of time it took me to get there, which is minutes. We're going to do over minutes right now. So that's 5 minutes. This would tell me how fast I was going. This would tell me how many miles per minute I was going. Okay? So the question is, could I make it a more precise number? Because that's an average over 5 minutes. And we all know that, you know, here in Montana, we've got ups and downs and lots of things that 1 minute I could be going 25 up a hill and the next minute I could be going 60 down the hill, right? So 5 minutes is a really long time to find an average. What if I made my interval shorter? Would that give me a more precise number for how fast I was going at an instant? Well, yeah, that would give me closer to the exact number, right? So what if I did this at 2:02 and 2 minutes? That would give me a much closer approximation of how fast I'm going right at 2 o'clock, right? But I want to get even better than that. So I'm going to go at 2:01 and 1 minute. Okay? And I can get even better and better. And so the question is, how do I mathetize this even a little bit more to figure out how I can get right up to 2 o'clock? Because I can keep making this interval shorter and shorter and shorter, but how would I write that with math? So let's take a look. Okay, so think about my distance at 2:01 is really my distance at 2 o'clock plus my change in time. Remember, this little triangle means change, or we call it delta. So this is delta t. So my distance at 2:01 is really whatever my distance was, or let's see, 2:01 is really 2 o'clock plus whatever the time changed, right? However much time actually changed. So instead of writing 2:01 in here, I could just say 2 o'clock plus whatever my time changes, because then I wouldn't have to keep changing it, right? I could just say, okay, now my time changed. First it changed by 5 minutes, then it changed by 2 minutes, then it changed by 1 minute. Then we can go to half a minute. So we can just keep making that delta t smaller and smaller without having to rewrite our numbers every time. So I could say the distance at my new time minus the distance at my old time over however much the time actually changed, right? Because before it was at 5 minutes, I put 5 down here. So now I say, well, what if I just make this delta t really, really, really small? What if I make that as small as I possibly can to get to close to 2 o'clock? Well, we know what that looks like in calculus. We've been doing it. The limit as delta t approaches 0, right? I'm trying to get this number to 0. I'm trying to get it to nothing, right? But I want to get it really close to nothing, but I don't want to get it right. I can't put it at nothing, because here's the question. If I put 0 in here, I would get an indeterminate form. I'd get 0 over 0. That would give me nothing. I wouldn't understand what to do with it from there. So we're going to find the limit as it gets really, really, really close to 0. And basically, that's what we're doing when we're finding the tangent line. So if you can imagine, you know what, let's do a different function, one that actually maybe represents something. Okay, so here we have a function, and this might be the function of my speed over time. And I want to figure out, what is my speed at this exact point, right? How much is my speed changing at that very moment? Well, that would be we would use a tangent line to find what your speed is at that exact moment. But up until now, we don't have any tools to find that tangent line. We don't really know how to find an instant rate of change, but we do know how to find an average rate of change, right? I could say from this moment to this moment, say this is 2 o'clock, and this is 2:05, I could draw a line through those, and I would say my change in y, which would be 2:05 minus 2 o'clock, right? Because that's my delta y, over my change in x, which would be 5 minus 0, which is 5. I could find that, right? Okay, well in calculus, we know we can just take the limit. Instead of having these 5 minutes apart, let's make them 1 minute apart. And do you see how that gets closer? If I start from 2 o'clock to 2:01, I am actually a lot closer to that tangent line. Well, then what if I do them half a minute apart? Should have used different colors. Okay, so if I make them half a minute apart, see how that's even closer to that tangent line? So if I make the change in between these two numbers really, 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 really small, then I'm going to be able to get really close to this tangent line. In fact, I'll be able to find it if I find the limit as it approaches 0. So that's where our limit definition of derivatives comes from. The derivative, f prime of x, which remember is the slope, the function for the slope of the tangent line, f prime of x equals the limit as delta x approaches 0 of the y value of our function minus the initial y value over our change in x. So let's describe what each one of these means. Okay, so look, do you see how these are very, very similar? So really we said, here's our initial value, here's our new value, right? This is our first point, this is our second point. And to figure out how far we went from this point to this point, we take our original function and we add delta x to our x's, right? So this is this point and this point. The change in x is this value right here. Okay, so this is our delta x. And what we're trying to do is we say, okay, to find the average rate of change, we take this and we subtract this and then divide it by our by the time that it took, by our change. Now, if we get this delta x to get really, really, really close to 0, then we're getting those points, instead of being far away, they're getting closer and closer and closer to 0. But again, we can't plug 0 into this because we would get out 0 over 0, which is an indeterminate form. So we use the limit as delta x approaches 0. So that's where this whole thing comes from. You might also see it as the limit as h approaches 0 of f of x plus h minus f of x over h. It's the same thing. You see, instead of delta x, I just use h because delta x gets really messy, so it's really difficult to keep delta x, to understand why delta x is doing what it's doing, and to remember that that's delta x and not x, and anyway, it gets messy. So sometimes you could just write it as this. It's the same exact thing, just with an h. So I hope that gives you a little bit more understanding about where derivatives came from and how the limit definition of a derivative actually tells us something about the function.